Hello and welcome back. In this video, we are going to look at basic regression using the Auto MPG dataset, and we'll try to predict the fuel efficiency. So in the previous video, we looked at text classification, where we tried to find if a review was positive or negative. In this case, we are going to look at regression problem and try to predict based on the features for a vehicle, what would be the miles per gallon for that particular vehicle. And again, this particular example and code is directly from the docs in TensorFlow. Here is a link to that, and I'll be simply copying the code and explaining the code as we go through this. So the first thing we need in this case new, that is Seaborn library we'll be using, and if you do not have that installed, you may have to type pip exclamation mark pip install -q Seaborn, and that should install the Seaborn library. Again, as you'll see, after the runtime is connected, I'm not using the GPU in this case. It's without the GPU. If you need the GPU, I'll switch over to that runtime later on. So here this kernel is connected, and we have, let's see how much RAM we have this time. We have around 12 GB of RAM, and so now we can go ahead and look at the install. So install for Seaborn is done. We can now import the libraries. So let's do that. Import matplotlib.pyplot as plt, import numpy as np, import pandas as pd, import Seaborn as sns, and in addition to this, we'll set the numpy print options np.set underscore print options precision is equal to 3 and suppress is equal to true. So what this will do is we won't get the numbers in scientific form, and we'll are limiting the precision to just 3 decimal places. Additionally, we need to import TensorFlow as tf, and then from TensorFlow we need to import keras, and from TensorFlow.keras we need to import layers. And we can also print the version of TensorFlow. So print tf.__version, and down below we should see the version, and this is TensorFlow 2.11. And now for the Auto MPG dataset. So let's create a heading here. Download the data. Download the Auto MPG dataset. And for this, we'll use the URL that we'll download from the UCI machine learning repository. So URL is equal to http://archive.ics.uci.edu ml machine learning databases auto mpg, and then auto-mpg.data. That's the file we need. And in this, so that's the URL. And now we need the column names. So the column names are going to be these, is equal to, we have mpg, that's the miles per gallon, which we are going to predict. Next is cylinders, number of cylinders in the engine, displacement of presumably the piston, then horsepower of the engine, and then we have the weight of the vehicle, acceleration of the vehicle, and then we have the model year, and after that we have origin. So those are the column names, list of columns names that we have created. And now we'll get the raw data set using pandas library pd.read_csv. using the URL directly, and then we'll specify the names is equal to column underscore names. We'll specify na underscore values is equal to question mark, and then comment is equal to, we have a tab there, \t, and separator is equal to this just space, and skip initial space is equal to true. And with this we can also print the shape of this. So raw underscore data set dot shape, and so let's see what we get. Oh, there's a typo, na values with a e, and again there's a type, oh sorry, my mistake, and the name raw data set, uh, again there's a typo, raw data set with a a. Okay, so we have around 398 records and 8 columns. We can now create a copy of this. So let's create a copy. Dataset is equal to raw underscore dataset dot copy, and dataset dot tail. Let's look at the last records, last 5 records in this dataset. These are the records: miles per gallon, cylinders, displacement, horsepower, weight, acceleration, model year, and origin. And we can look at the data type, dataset dot dtypes, and here we see that these are all numeric values. Next, we can also look at are there any missing values in there? So how many missing values per column? So dataset dot isna, that creates this mask of Boolean mask, or true or false, and we can get the sum for the true values that are there, and we see that there are 6 missing values in the column horsepower. So we could decide based on situation what we want to do. In this case, we are simply going to drop those missing values, and we'll create the data set with no missing values. So we'll say dataset dot drop na, and now if you look at the shape of dataset dot shape, we should have 2 less rows. So earlier we had 398, 6 less rows, and now we have 392 because we dropped the 6 missing columns. Next, if we look at the column origin, if you look at data set, and if you look at the column origin, and these are the values we have. We look at the unique values. We can say dot unique, and we see that there are 3 unique values in that column, 1, 3, and 2. So we can assign a letter to this. We can say 1 is USA, 3 is Japan, 2 is Europe. That's based on the information in the data set. And we can map those values and then create dummy variables for those. So let's see how we can do that. For this, what we are going to say is data set origin. So we are going to replace the values in the column origin, and using the values in the same column origin, and then to this we are going to say dot map, and here we'll say 1 colon USA, and then we have 2 colon Europe, then lastly we have 3 colon, this is Japan. And now if you look at the data set, we should see that in the column origin, instead of 1, 2, 3, we now have these names of regions listed. We can now use these names and inbuilt methods in pandas, which is get dummies, to create one hot encoded columns. So what we'll do is say data set is equal to pd.get underscore dummies, and inside of this we are going to specify the column that we would like to get converted to one hot encoded value. So USA would be a column with once if the row has a value of USA, otherwise it will be 0. Same thing for the other two regions. And here we'll say data set, comma, columns that we would like to convert, which is in this case the origin column. And then we need a prefix for the new column that is created? We won't need any prefix, so we just leave that as just quotes, and then again prefix separator, or as it will attach to the actual value inside of that column. There's nothing, so we just leave that as that. And then we look at the last records from that particular table after we create the dummy values is dummy columns is this. So now, as you can see, the first column at index 0 has value of USA. So, let's look at the last one. Last column has a value of USA, and so if we last row has a value of USA, and if we look at this last row with the index 397, we have a value of 1 in the column USA, and the columns Europe and Japan have a value of 0. So likewise for the index 394, this Europe. The index 394, what we have is a value of 1 for Europe and 0 for Japan and USA. So with this done, we can now split the data set. So let's do that. What we are going to do is split the data into train and test set, into train and test set. Okay. So for this, train underscore data set is equal to dataset dot sample. We are going to randomly select 80% of the data for the training purposes, and we'll set the random underscore state is equal to 0 for reproducibility, and then we'll create a test data set that would be all the rows that are not in the train data set. And for that we'll say dataset dot drop train underscore dataset dot index. There are different ways to do this. This is one way, and here again we can look at the shape of train underscore dataset dot shape, and we can look at test underscore dataset dot shape, and we should see that we have 314 in the train set, 378 in the test set, and if we add these two, 314, and if we add these two, we get the total 392 that we started out with. Now, looking at the data, before we get started on the analysis side, we can inspect the data. So inspect the data or explore the data. And in this case, what we are going to use is the Seaborn library, and we'll create what is called a pair plot, sns.pairplot, and this will use the train data set, and from train data set we'll use these columns: miles per gallon, cylinders, displacement, and weight, because these are the features that are going to directly affect the, at least we think that they will directly affect the miles per gallon of a vehicle. And for the histograms, we are going to say that this is going to be a KDE plot, and when we run this, we should see a nice grid plot of 4 by 4, and within this we'll see we can see the relations between different features. So as we see here, for miles per gallon in the first row, we look at the displacement and weight. There is some relation. So as the displacement increases or as the weight increases, the miles per gallon does seem to go down. And number of cylinders, in case of number of cylinders, it seems that as the number of cylinders is increasing, such as here, overall the miles per gallons seems to be reducing. So maybe a larger vehicle, powerful engine, more cylinders you have, more horsepower you have, more displacement, and thus more weight of the engine and the vehicle. And so the miles per gallon could go down. So that's one interpretation. And diagonally, we see that these are the KDE plots where we can see how the data within that column is distributed. So for example, for weight, we see that it's a little bit skewed, and there's most of the weights of the vehicles in the data set are between this range around 2000 to 3000. With that, now we can look at the descriptive statistics of this data. We can say train underscore dataset dot describe, and if we look at this data, this result as is, we get the values with column names up top and the statistics on the as column as row indices. We could transpose that, and we could say transpose, and now we can see that the statistics are up top and we have the column names on as row indices, and we can see what is the count, mean value, standard deviation, and the other quartiles. So one thing immediately that we'll notice is that the scale of values is much different. So weight is 4-digit values, whereas cylinders is just a single-digit value. And we'll come to that when we talk about normalization. And now let's move on and look at how we can separate these labels. So labels is in the miles per gallon column from the rest of the data set before we can begin any type of training process. So split the features from labels, or in other words, we can say separate the features from the target values. Oh, and let's put a space there so we get 3 separate lines. And for this, we'll say train underscore features is equal to train underscore dataset dot copy, and copy, and after that test underscore features is equal to test underscore dataset dot copy, and then labels. So train underscore labels. This is an easy way to kind of separate the column that we are trying to predict. Train underscore labels is equal to train underscore features. We simply say pop, so that will remove the column from the existing dataset, and we are assigning it as a label mpg. And likewise, we have test underscore labels is equal to test underscore features dot pop, and we say miles per gallon there and run this. So now if we look at the shapes, again print train underscore features dot shape, and print test underscore features dot shape, and again we can look at print train underscore labels dot shape, and print test underscore labels dot shape. And we see that the number of labels and features in the train is 314, and it is 78 for the tests and dataset. All right, with that, now we are in a position to perform normalization. So let's look at that normalization. And the idea behind normalization is to bring these values that are in completely different scale to a similar scale. So these are 4. This is a very small number as compared to the number that we have in the column weight, and likewise for the other columns. So for normalization, what we'll do is say train underscore dataset dot describe, and this is just to taking another look at what we have already seen. Transpose, this is what we get, the statistics that we saw, and from this we are going to pull and look at just the mean and standard deviation, and this is kind of a mean and standard deviation, so STD, not SD. So let's correct that. There should be a T in there. So as we can see, the numbers are at a different scale. So for normalization, we'll create a normalization layer. So normalization layer, and for this we'll create a variable normalizer is equal to tf.keras.layers.Normalization axis is equal to -1, and to fit this to the data set. So this is the layer we created. Now what we are going to do is fit layer to data, and for fitting this normalization layer, we are going to say is normalizer dot adapt, and adapt, we cannot say train underscore features directly because it's a data frame. What we need to do instead is convert this to a numpy array. So what we are going to say here is np.array, and so we should get the normalization. We would then be able to adapt it. So before we run that, just wanted to show what we are converting. So here's our data frame, and if you look at the type of this, it is a data frame, pandas data frame. Now what we are going to do is convert this to numpy array. When we convert this to numpy array, this is what we get. We just have a nice array structure with numeric values in it. So once that is fit, we can print the mean and variance that were calculated within the normalizer object as a process of running normalization on the trained features. And so we can look at mean and variance after the fit, and to get that we simply need to say normalizer. So we can print normalizer dot mean dot numpy, and so let's see what we have. Normalizer dot mean, normalization object does not have value of mean because I haven't run that yet. Okay, these are the mean values that we have for the dataset. So with this done, what we can now do is see how this would apply to our dataset. So what we'll do is create an array np.array train underscore features, and we'll just use index of 1. We just need one set there, and we'll call this first is equal to this. And if you look at what's in the first is these are the values. So if you look at the array that we had created, so if you look at this array right here, this is the first row that is there, and that's what we are looking at up in the first variable that we created. So for that first row, we are now going to apply the normalization. So here's what we'll write: with np.print options precision is equal to 2, suppress is equal to true, print first example first, and then print open close parenthesis, print normalized and normalizer first dot numpy. And we should see, so what we have here are two things. These are the original values that we have up here, and these are the normalized values that are normalized using the layer that we just created. So we are using the normalizer here, and we are then converting it to numpy. So let's now use all of this to perform the linear regression. So I'm going to create another heading here. It says linear regression, and we'll increase the font size there. So that's that. And the first linear regression that we'll do is going to be with just a single feature. So linear regression with one variable. And this is just to see the impact of having more data on how accurate values we get. And the very first variable that we are going to choose that's in the docs is horsepower. And so we'll use the variable horsepower, and we'll say np.array train. And so what we are doing is taking the data, taking the column horsepower from the train underscore features and converting it to an array. So horsepower, that's there. And so now what we have is horsepower. These are the values that we are going to use. This array is what we are going to use to perform the prediction of miles per gallon. And before we do that, so here we'll put small headings here. This is our data. Then we are going to perform normalization, and for normalization we'll use horsepower again, and the layer that we normalization layer. So horsepower underscore normalizer is equal to layers dot normalization input underscore shape is equal to 1 comma, and then we have axis is equal to none, and then we'll fit this horsepower underscore normalizer dot adapt horsepower. And so once that is done, we can now build our model. So build model in Keras. So horsepower model is equal to tf.keras.Sequential open close parenthesis open close square brackets, and the normalizer will be the first layer. So horsepower underscore normalizer, and then the next layer we'll have is layers dot dense. We just have one layer in this case. Dense units is equal to 1, and then we can get the model summary. So horsepower underscore model dot summary, and so that's a typo there, or normalizer. And now when we run this is the model we have. It's a sequential Keras model in Keras, and we have two layers. The first layer is normalization layer, second layer is a dense layer. With this model then, without going into the training part of it, we can directly use that to make a prediction. So we could predict by saying simply horsepower model dot predict, and we have horsepower, we'll input a value. So this value, so the value that we are going to use in this case is just this value. Sorry, should be 10, and the value we have is this. So this is the array, and once we input the values, here are the predictions for those. And these values, again, we can see that the output is not good, and that's because we haven't done any training yet. So let's now do, so this is without training. Let's now compile the model. So for compiling the model, we can say horsepower underscore model dot compile is equal to optimizer. So we need two things. So first one we need is optimizer, and the second thing we need is loss. What is the loss function we want to use? So for optimizer, because this is a regression problem, we are going to use the Auto optimizer, tf.keras.optimizers.Adam, and we'll say the learning underscore rate is equal to 0.1, and for the loss we are going to use the mean underscore absolute underscore error, and that's how so there's a problem. Let's see what this is. Invalid syntax. Let's see. Our model.compile. Oh, my mistake. There shouldn't be an is equal to there. That's my mistake. Okay. So horsepower, we have compiled the model, and now we are ready to fit the model. So we can perform the fit, and the time it takes to fit to run this cell, we can use time % time to check that. So here's the history. History is what will store the information during the training process for each epoch. Horsepower underscore model dot fit, and here we need to provide a bunch of information. First is train features, and this in this case, because we are working with just one feature, horsepower, we'll just specify that. Next we have the train labels, then we have the epochs is equal to 100, and then verbose is equal to 0. So what this will do is, do we need any output like when the training is going on? And so we are setting it no. And then we have the validation split. Validation split is 0.2. So what this means is that the validation would be performed on the 20% of the trained data set. So now we can run this, and once this is done, we should see the time it takes to run this. So this took around 4.8 seconds. And now with this, we can look at the history to see what was the validation loss, what was the training loss, etc. So for that, we'll create a variable hist that will say pd.data_frame, and we'll use history.history. And inside of this history, we'll also create a column called epoch is equal to history.epoch. And now we can look at the last rows in this particular data frame history. So his.tail will have the last 5 records, and we see that the validation loss, and we might as well look at the head, that is the top 5 records. And as we can see, the validation loss started out with 22.9. It came down to 4.141, and by the epoch 1 number 99. So that's the 100th epoch, and so that's what we have in this case, using just one feature. And if we were to plot how the loss looked like, we can use the matplotlib, right? We create a function plot underscore loss history, open close parenthesis history, and inside of this we'll say plt.plot history.history loss, and label is equal to loss. So that's one, and then plt.plot history.history validation loss. Again, here we can specify the label as validation underscore loss. And finally, we can set the limits, plt.y limit. So y-axis, we want that to go from 0 to 10, and plt.x label. The x label is number of epochs, and plt.y label is the error for the predicted error between the predicted and actual value for the miles per gallon. Plt.legend, that will tell us what line that we plot is for what. And finally, plt.grid is equal to true. We'll set this to true so that you can see how those lines plateau. And once this runs, we should be able to now plot it. by simply calling that function plot underscore loss history, and here is the plot we have. Epochs, as the number of epochs grow, we see that the loss starts to go down, and by the epoch around 30, this kind of both the validation loss and the training loss stay constant. They do not decrease any further. And another point to note is that the validation loss is lower in the sense that it doesn't decrease as much as the training loss, and that is expected. So is there anything we can do to bring the validation loss further down? And maybe we could what we could do is add more features, and we'll see that in few minutes now. But before we do that, let's look at the test results. Test underscore results is equal to create a empty dictionary, and again here we'll use the dot evaluate to perform the evaluation. So we'll say test underscore results horsepower underscore model is equal to horsepower underscore model dot evaluate open close parenthesis test underscore features. We just have one feature, that is horsepower, and associated labels test underscore labels, and labels, that's that, and then we say verbose is equal to 0. So when we run this, so this would perform the evaluation, and now what we can do is again get ready for the predicted values. X is equal to tf.lean space 0.0 comma 250 comma 251, and then y is equal to horsepower underscore model dot predict x, and this will do there's a typo, predict with a letter T. And now so that's done. Now we can again create a scatter plot. So I'm going to simply copy this, paste it down here, and instead of loss I'm going to say horsepower. So we want to see how the predicted values compare with the actual values, and here are the values that we are looking at, kind of a range, arbitrary range, for which we are trying to get the predictions. We are choosing this range because that's the range in which we have the data. And so horsepower, and we'll use the scatter plot. So plt.scatter, and let's remove all of this, delete that, and say train underscore features horsepower, and then we have train underscore labels comma label is equal to data. So that's the actual data we have, features with the E, that's actual data. And next what we are going to do is plot the predicted value. So plt.plot, this is going to be a line now, x comma y color is equal to k, so it stands out on the scatter plot. Label is equal to predictions, and again the x and y labels, we need to change those. So x label in this case is going to be the horsepower, and the y label is going to be simply the miles per gallon. And we do need the legend, we do not need the grid in this case. So with that function ready, we can call that function plot underscore horsepower x comma y, and we should see a nice scatter plot horsepower. So what's missing? Look at so horsepower, it's the takes one positional argument, 2 were given. Oh right, forgot to change this, x comma y, and now we should see, okay, scatter, again a typo, a double T, And now what we see is a nice plot where we have the horsepower on the x-axis, miles per gallon on the y-axis. As the horsepower continues to increase, the miles per gallon does go down, and the prediction also says that it does go down, but then the black line does not follow the data set right at the beginning, at the end. So it's a straight line, it is not a curved line. So we can do better, and let's see if we can do better using multiple input features for this regression model. And so we'll say linear regression with multiple inputs. And for this then we'll again use the linear model. Linear underscore model is equal to tf.keras.Sequential, open close parenthesis, open close square bracket. The first layer is the normalizer, and then we have the second layers dense, and with units is equal to 1. So with that, so we create a model. So let's give this a heading. What we are doing here is create a model and run that. And with that model, with now that we have created, we can call the predict method. So this is predict, and linear underscore model dot predict train underscore features colon 10. And again, if you look at train underscore features colon 10, let's look at that here. We see that we have more than one feature this time that we are using, and those features are input to the predict method, and these are the outputs we have. Again, this is prediction without training, and so the values are off a lot. And what we can do now is compile the model. But before we do that, we just want to look at some values within this particular model. So we'll say linear underscore model dot layers square bracket 1 dot kernel. And so what this is telling us is the values that are within the kernel, and this is of shape 9 by 1. So this would be sort of the weights or coefficients that are currently for the linear model. We can now compile. So compile the model, and for compiling it's the same setup, dot compile and open close parenthesis, and here we specify the optimizer is equal to, and then we specify the loss is equal to. For optimizer, we again will use the Adam optimizer, tf.keras.optimizers.adam, and learning underscore rate, will set this to 0.1 and need a comma. And finally, for loss, we'll use the mean absolute error for the loss. So let's run this. That will compile our model. Then it's time to fit the model. And for fitting, we'll again time it and say history is equal to linear underscore model dot fit. And inside of this, we have train features. So this time, all the features, train labels. So all the labels, of course, are going to stay the same. Epochs is equal to, we say 100 epochs. Verbose is equal to 0. So we stop any output during the training. Validation underscore split. So 20% of the train data for validation. And when we run this, this will perform the fit on the more than multiple features. And with that history, now we can use the function that we had created earlier. We can simply plot the loss, plot underscore loss, and we'll use the new history that we have from the multiple variables. And as you can see, with more data set, more features, multiple features, we were able to bring down the validation loss. As you can see here, earlier there was this gap between the validation orange and the blue training loss, but now they are almost the same. So that is a good sign. Now we can again test the results on the test dataset. We can say test underscore results linear underscore model and is equal to linear underscore model dot evaluate test underscore features test underscore labels verbose is equal to 0. So that is done, and as we did earlier, so if we scroll back up, so these were the results, and what we can do then is we can again use the same setup right here, and instead of the horsepower model, we are now going to use the a linear model, but again we cannot use that because earlier that setup worked because we just had one feature. Here we have more than one feature, so let's skip that part. Now another variation that we can do to improve the performance of a model is adding more layers to our neural network. And so the heading is regression with a deep neural network, DNN. And what we are going to do here is add two more layers. So we are going to add more hidden layers. And so here's the model DEF build and compile, or let's do it this way. We'll create a model. Model is equal to tf.keras.Sequential open close parentheses, open close square brackets, norm, that's the normalization layer, comma, layers dot dense 64, comma, activation is equal to relu, and then we have layers dot dense, and then we have 64, activation again is equal to relu. Finally, we have layers dot dense, just one value, and this is going to be our model. And then we'll compile this model dot compile loss. Again, here we have the same setup. Optimizer is equal to tf.keras.optimizers.atom, and learning rate is equal to 0.001, and the loss is going to be mean underscore absolute underscore error. So it's the same setup that we had earlier. Now one difference being, what we are going to do is put all of this inside of a function so we can reuse this model. So what we'll do is type here def build and compile model, and this just takes a different normalization layer. Okay, so that's where the norm comes in, and we are going to return the built model. So that's the function which is now ready. What we are going to do is use the we'll perform the fit using just the single feature and multiple features. So the first one is, let's create a heading. First one is regression using a DNN and a single input. Okay, so that's what we are going to write. The DNN underscore horsepower underscore model is equal to build and compile model and horsepower underscore normalizer, and so this is what we are building a model. So let's put a heading there. model. So build model. That's what we have done. Next thing, okay, so there's an error. Let's figure out what. Dense has no attribute layers. Okay, so sequential, sequential norm layers.dense, and what we are saying here is build and compile model horsepower underscore normalizer, but then, oh right, my mistake. So here there should be a comma, and now this should work. So we have built the model. We are now ready to look at the model summary. So model summary is just going to be dnn underscore horsepower underscore model dot summary, and that gives us this summary that we have. And with this summary, we can see that we now have these two additional layers in there. We can now fit the model. Again, we can time it like so, time, and let's say history is equal to dnn underscore horsepower underscore model dot fit, and this takes in train underscore features, and just one features. There's a horsepower with a capital H, horsepower, and we have the labels for the train underscore labels, validation underscore split, the same 20%, 0.2, and we have verbose is equal to set to 0, and epochs is equal to 100. So that's the fit that we are doing here. And once the fit is done, we should be able to plot the loss. And so we have a wall time of 6.99 seconds. Plot underscore loss history. And again, in the plot, we should be able to see the difference between the validation loss here in the orange and the training loss here in the blue. And we see that the validation loss could be brought down further. So adding more hidden layers in the neural network with a single feature doesn't really seem to help much. And if we now try to plot the data with this on a 2D plot, because we have one variable, we have the advantage of creating the plot in 2D. So let's create a set of test variables x, and then use our new DNN horsepower model to predict the values in y. And once we have this, we can now plot this. So this is what we have is for this set. Let's just say test set for this one, and we can now plot this. So plot underscore horsepower x comma y. And as earlier, what we saw was we just had a straight line. If you look at the earlier scatter plot, this was just a straight line going through the cloud of points. However, with more layers, I think we have introduced some nonlinearity in the model, and we see that it is trying to fit the data and trying to match the contour of the shape of the data cloud that is there. We have a curve down below in this particular plot. We can now evaluate the model. Test underscore results dnn underscore horsepower underscore model is equal to dnn underscore horsepower underscore model dot evaluate, and we have test underscore features horsepower, and then we have comma test underscore labels comma verbose is equal to 0. So that's going to give us the test result. So it's the same setup that we had earlier after we performed the fit prediction on using a single feature. Now moving on, let's take this a step further and perform the regression using a deep neural network. and multiple inputs. And one would hope that with more data, more deeper neural network, we would get a better result. So DNN model is equal to build and compile underscore model normalizer. That's what we are going to use for normalize. And so that's what is going to, this is, oh, so let's run that. Here we can add a heading build model, and after that is done, here we can add later model summary, and we can say dnn underscore model dot summary, and we have the summary there. We have nice two layers, extra layers there. We have trainable parameters that 4865. Earlier, we had trainable parameters that were 40353. Now we can again perform this part. So I'm going to simply copy this, paste it here, and this time this is going to be DNN model fit. And instead of horsepower, we need all those features. So delete that. Rest of the code stays the same. We run this and this will perform the fit. Once the fit is done, we can plot the loss. So plot underscore loss, and we have the new history that was created here. Again, this took 6.6 seconds with all the features. If we look at the earlier, it took 6.99 seconds. So about the same time. And now when we plot the loss, we should see the gap between the validation and prediction reduced. But in this case, if we go back up in this here, we have the error that was around just below 4 for validation. Here the error for validation has come way below 4. It has reached close to 2. But then the training loss also decreased, and therefore we still see the gap between those two. But overall, the validation in this case with multiple features and more layers, we definitely improved the score. We did improve the performance of the model. So now let's look at the performance. And here we can create a data frame test underscore results index is equal to mean absolute error MPG, and we are going to, so this is going to give us a data frame that looks like this. We can use the .t in front of it so that we get a nice layout as we see here. So the horsepower model gives us a mean absolute error of 3.65. The linear horsepower model gives us 2.4, and then DNN gives us uh, mean absolute error of 2.8. And now if we try to plot the predictions again, so let's come down here and say make predictions. So for predictions, so predict test underscore predictions is equal to DNN model predict DNN model dot predict test underscore features, and they can say dot flat. This is going to give us this. So test underscore predictions, and so these are the values we get. We can flatten this dot flatten, and so after we flatten it, we get the values in this form, which we can now use to create a plot. So for plotting, we'll say A is equal to plt dot axis aspect is equal to equal, so we get a square plot, and that's because we are gonna try to see how y changes as we change the values on the x-axis. plt.scatter test underscore labels comma test underscore predictions. So the predictions, we have the original values on the x-axis and predicted values on the y-axis. plt.x label, so we are looking at the labels true values mpg, and then we have plt.y label, and here we have predictions, again mpg, and we set the limits. Lims is equal to 0 to 50, and we are going to use these limits in x and y both because we are trying to create a square plot. So plt dot limits is the same, plt dot y limits, it's going to the same limits, and we are finally ready to plot. So we'll say plt dot plot lims comma lims. So we'll be plotting that, and now when we run this, we see a nice plot where the true values and the actual values seem to uh, kind of correlate with each other, and we see that this blue line goes through most of the data points except for these up here. They seem to follow that 45-degree line that's going through the going through there. Okay, so that tells us how good our predictions are, and we could also look at the distribution of the error. Again, that's a nice check to look at. Error distribution, and we'll say error is equal to test underscore predictions minus test underscore labels plt dot hist error, and we'll set the bins to 25 bins. This is arbitrary. plt dot x label prediction error in miles per gallon. That's what we are getting a histogram for, and this is plt dot y label count. And when we run this, we see this is the histogram of the errors. That's the difference between the actual and predicted values, and we see that the difference is between plus minus, most of it is between plus minus 2 miles per gallon. And if we look at the histogram for the for our data set, so the data set, let's see, let's go back. That's going to be just the train y. So let's say let's go back up as train labels. Let's look at train labels. Train underscore labels, and this is what we have. So the lowest miles per gallon is 10, highest miles per gallon is 45. We look at the test labels. If we look at the test labels, these values are about the same range, 10 to 45. And so what this is saying is that the plus minus 2 miles per gallon difference, it looks like it's not too much of an error. Again, it's relative, but looks like we are doing okay with the model that we have, and maybe there's still more room for improvement that could be done with further optimization. Now, once we are done with the model, and let's say that model is final, what we can do is save the model. And to save the model, we'll say dnn underscore model dot save, and we'll specify the name for the saved model, dnn underscore model. That's what we have. And just a final check, we can reload the saved model, and look at how the reloaded model does. Reloaded is equal to tf.keras.models.load underscore model, and here we have dnn underscore model, and Now that's a reloaded model, and we say test underscore results reloaded is equal to reloaded dot evaluate, and here we have test underscore features, test test underscore labels, verbose is equal to 0. And with that, we can put all of this stuff in a data frame. pd.data frame with a capital D and F, test underscore results comma index is equal to mean absolute error, and this is miles per gallon, and then we put a transpose T at the end, and here is what we have. The reloaded model for some reason is performing better than the original model, but yeah, so that's actually not the original model, but that is performing better than the other models that we had above. So what we have here is the DNN model. And so in the end, we can see that using more features uh, could help improve the accuracy, bring the validation loss down. Again, we could use different types of loss functions. So here we use mean absolute error. We could use mean squared errors or other metrics for evaluation. And another point to note according to docs is overfitting is a common problem with deep neural networks. Uh, what it means is that as the the model fits well to the training data, but does not generalize well to unseen data such as the test data, and so the predictions are off in the unseen test dataset. In this case, still the model did seem to do well on the test dataset, so maybe the overfitting was not a big of an issue in this case, but that is something that one needs to look at when working with deep neural networks. So that was it for this video. I hope you enjoyed this video where we looked at a regression model in different scenarios, how we can use Keras libraries to perform the predictions. If you have any comments or suggestions, please do let me know in the comment section below. I hope to see you all in the next video. Please like, share, and subscribe. Thank you.